In the last class, we have discussed 2D and 3D Bravais lattices and different type of structures like simple cubic, face-centered cubic, and body-centered cubic, hexagonal closed bracket structure. We have discussed different crystal structures. Now, in this class, we are going to discuss the atomic packing factor of or APF of simple cubic, body-centered cubic, and face-centered cubic structure, because this is one of the very important topic. If you go through the previous set papers, you can see that in the set papers there are 7 to 10 questions from the condensed matter physics, and if you go through the previous case set papers or any other state set papers, you can find there are many questions related to atomic packing fraction. So this is one of the very important topic. And also if you go to the previous CSIR net purpose, in the CSIR net there maximum there are 2 or 3 questions in the part C, and this crystallography is also one of the important there. Okay, so today we are going to discuss, in this class we are going to discuss atomic packing factor. So what is atomic packing factor? Atomic packing factor, APF, means volume of atoms in a unit cell upon volume of unit cell. So what this give us? This give us the data about how much fraction of the unit cell is occupied by the atom, how much is free and how much is occupied. Just like imagine you have a one cup, one glass, and you filled with half of the part you filled with milk. So the packing fraction is 50%, means 1/2. 50%, or in the fraction if you say that it will be 1/2, in percentage it will be 50%. So just like when we fill atoms in the unit cell, how much volume of this unit cell is occupied by the atom, that is given by the atomic packing fraction. So now here we are going to discuss the atomic packing fraction of 3 important type crystals, which is usually asked in our examination, which is very common in examination. If you go to the previous papers, we can find many questions related to the Bravais lattice and atomic packing fraction. Okay, so first we will discuss a simple cubic. Simple cubic we written by FCC. We know that in the simple cubic structure, in the last class also I told you that in the simple cubic structure we have only atoms at the corners. We have atoms only at the corners. At 8 corners we have atom at the 8 corners, and so in this figure there is an extra atom. No, there is no atom in the middle. We have only atoms at the 8 corners. Okay, and I told you that the atoms in the corners, when we draw the figure, we draw like this simple cubic structure to show that there is atoms at the 8 corners. In the last class we have also calculated the number of atoms in the unit cell. Every corner atom contribute 1/8 of its volume towards one unit cell. So total from 8 corners we have 8 into 1/8. Every corner contribution is 1/8. So we have 8 corners. So 8 into 1/8 is equal to 1. So total atom in a simple cubic structure is 1 atom. Okay, and I told you that normally when we draw in this way, but like in actually these corners atoms in the simple cubic structure, these corners atoms are touching each other. These spheres are touching each other. So in this third figure you can see that the contribution to the one unit cell. Now from this particular structure we calculate the volume of the occupied atom in the unit cell and volume of the unit cell. Okay, so we know that unit cell parameter we take for a cubic type structure, this A equal to B equal to C. So this unit cell, the length of the cube is A, height is also A, and breadth is also A. So the volume of the cube will become volume of the cube. Volume of the cube. Volume of the cube is equal to length, breadth into height. So A into A. So that is equal to A cube. So we got the volume of the cube. Now we want the volume of the atoms occupied in the unit cell. So volume of atom. Volume of atoms. So if the radius of one atom is r, what will be the volume of one atom? Because the atom have a spherical shape. So the volume of one atom will be equal to 4 by 3 pi r cube, where r is the radius of the sphere. So we have only one atom there. So 1 into 4 by 3 pi r cube. So now the atomic packing fraction is, we know that atomic packing fraction is volume of atoms upon volume of the unit cell. So 1 into 4 by 3 pi r cube divided by volume of unit cell is A cube. Now look, we have to write either r in terms of A or A in terms of r. We can do anything. You write r in terms of A or A in terms of r and cancel that term. Then we get to the actual APF. Okay. So here we write A in terms of or r in terms of A. Let us write r in terms of A. Look, in this figure you can see that this is touching each other. This sphere is touching. Look, this sphere is touching each other, and this is the radius of one sphere r. This is another sphere. So here also in this third figure also you can see, look, this is r and this is also r. So this A is actually here, you can see that this A is actually here r plus r. A is actually r plus r. So r plus r equal to A. R plus r equal to A, or 2r equals to A, or r equals to A by 2. Note the point, this is also asked in state eligibility test. R equal to in the simple cubic, FCC and body-centered cubic. They sometimes ask atomic packing fraction, sometimes ask R and A relation. Okay. So R is equal to A by 2. So now we write here, we can write this is volume of atom in terms of A. So here volume of atom become, volume of atom is equal to 4 by 3 pi r cube. So this will be equal to 4 by 3 pi into, in place of r we put A by 2. So A by 2 cube. So this become 4 by 3 pi into A cube by 2 cube is 8. So 8. So here 4 by 8 equal to 2. So this become pi A cube by 3 into 2 equal to 6. Pi A cube by 6. So volume of atoms occupied in the unit cell is pi A cube by 6. So now the APF become volume of atoms pi A cube by 6 divided by volume of the unit cell. So by A cube, volume of unit cell is A cube. So here A cube get cancelled, we will get a pi by 6. So note, if you go to the previous question papers, you can see that atomic packing fraction, if they are given in fraction, it may be either pi by 6. In terms of pi, they give pi by 6. If you put a pi equal to 3, pi is actual value, then this become 0.52. So it is pi by 6 or 0.552. In percentage, it is a 52%. So in the unit cell, 52% of the volume is occupied by the atoms. So how much is free space? 48%. So note this whole point, the R and A relation is R equal to A by 2 for a simple cubic, and atomic packing fraction in terms of pi is pi by 6, and in fraction it is 0.52. in percentage it is 52%. You must note all this point because if you go through the previous papers you can find these questions. Okay, so this is the atomic packing fraction for a simple cubic structure. Now we go to the body-centered cubic structure. In the body-centered cubic structure, we know that in the last class also we have discussed it. In the body-centered cubic structure, the atoms are occupying at the corners plus at the face center. Corners and face center. In the simple cubic, only at the corners. In the body-centered cubic, at the corners and the face center. So I told you that we have also calculated the number of atoms and we got the number of atoms. Number of atoms per unit cell. Per unit cell is we got 1 from the contribution, 1 from the all corners and 3 from the face centers. So total 1 plus 3 equal to 4. So those who didn't watch the last lecture, please note. We have 8 corners. 8 corners. And every corner sphere give 1 by 8 of the sphere. You can see in this figure also. Look, this is the part of a sphere. This is actually 1 by 8 part of a sphere. So every corner atom give 1 by 8 to 1 unit cell. Okay, because every corner atom is actually shared by 8 unit cells. So 1 by 8th part will be given to 1 unit cell. So the contribution to 1 unit cell is 8 into 1 by 8. So 1, 1. And every face center atom, look, this is a face center atom. The face center atom is actually half part is in a 1 unit cell and half part is in the for this particular atom. There will be a unit cell above it. So half part to go to that unit cell, half part to this unit cell. So every face center atom 1 by 2 part means a half part to 1 unit cell and half part to another unit cell. So how many faces we have in a cube? We have 6 faces. We have 6 faces and every face is 1 by 2 means a half part of a sphere. So 6 into 1 by 2 equal to 3. So how many atoms total in the unit cell? 1 plus 3 equal to 4. So there are total 4 atoms. Now look, same. Volume of the unit cell is same. Volume of unit cell. Volume of unit cell is equal to here also. It is a cube only. Even though it is a face-centered cubic. The shape of the structure is a cube. So volume of the unit cell is equal to a cube. Now we want to calculate the volume of atom. Volume of atoms. Volume of atoms. How many atoms are there? 4 atoms. What is the volume of one atom? 4 by 3 pi r cube. Now we want to write this r in terms of A. Okay. So now look. Last class also I told you that in the face-centered cubic, in the simple cubic structure, the corners atoms are touching each other. But in the face-centered cubic, as seen in this figure, the corner atoms are not touching each other. But which atoms are touching? The face center atom is touching with the corner atoms. So this face diagonal, if you go to this is the face diagonal, you can see that these atoms along the face, the atoms are touching. The corner atoms are not touching because there is a gap. You can see in the figure also there is a gap. So here look, this much is A. Here I am using blue color. This is R, radius of a sphere, and this half part is an R. This is a R, and this part is also R. So the face diagonal length in terms of radius it is 4R. Face diagonal in terms of radius is equal to 4R. So 4R equal to, in terms of A, look how it will be in terms of A. You know that this is a edge length is for a cube is A, and this edge is also A. So this is A, this is A. So this is the hypotenuse of this triangle, A and A. So according to Pythagoras theorem, hypotenuse become under root square of other two sides. So under root A square plus A square equal to root 2A. So look at this become, here I am writing under root a square plus a square. So this become under root 2a square. So under root a square equal to a. So root 2a. So in terms of a, the face diagonal length is equal to root 2a. So for r equal to root 2a. So r equal to root 2a by 4. This is asked multiple times. Okay. This question is asked multiple times. Very important. Sometimes they ask r equal to root 2a by 4 or a equal to 4r by root 2. Okay. So note here the face diagonal length in terms of r equal to 4r, in terms of a it is root 2a. From this we find the relation between r and a, r equal to root 2a by 4. Now we substitute this here, okay, and we will get the volume of atoms. So volume of atoms here become 4 into 4 by 3 pi into r cube. Root 2 cube become root 2 into root 2 into root 2. A cube of a equal to a cube, and 4 cube equal to 4 into 4 into 4. Okay. So now we can, here we have a 4, here 4 cancel. This 4 cancel. Here root 2 into root 2 equal to 2. So this become, in the numerator become 2 root 2. Denominator we have 3 here we have 4. So 2 root 2, here we have pi a cube divided by 3 into 4 equal to 12. So 2 root 2 pi a cube by 12. Now 2 by 12 equal to 1 by 6. So this become root 2 a by root 2 a cube by 6. Root 2 a cube by 6. So the volume of atoms in the unit cell is equal to root 2 a cube by 6. Now the APF become volume of atoms root 2 a cube by 6 upon volume of unit cell. Volume of unit cell is equal to a cube. So upon a cube cancel. Here we have a pi also. Pi, this pi into pi. Okay, so a cube cancel. So we get root 2 pi by 6. So normally you will get this root 2 pi. 6 we can write 2 into 3. And root 2 by 2. 2 we can, okay. 2 is actually root 2 into root 2. So this we can write root 2 pi root 2 into root 2 into 3. So this root 2 get cancelled. So finally we will get a pi by 3 root 2. So the atomic packing fraction of a face-centered cubic is pi by APF is equal to pi by 3 root 2. This is asked multiple times. Not very important. Not only in the case set, in the different state eligibility test. Please note one point. Many students message me in our WhatsApp that sir, what about our state eligibility test? I want to tell you that across India, the state eligibility test syllabus is identical. Question pattern is identical. As I am giving the coaching, I know that if you go through the question papers across the state, we can find almost very similar question, and many questions there are same to same. Means in the one state eligibility test question is repeated in the other state eligibility test. So the question pattern is same, syllabus is question pattern, the syllabus is identical. Okay. So pi upon 3 root 2. So in fraction this become 0.74. In percentage this becomes 74%. So for a face-centered cubic structure, atomic packing fraction is pi by 3 root 2. In the fraction, if it is asked 74%, also not for hexagonal closed packed also it is 74%, and this is asked in many examination that the highest packing fraction is 74% only. There is no such structure that we can have more than 75% occupy in the unit cell. That is not possible. So the maximum packing fraction is 74. So that too for FCC and HCP structure. For other structure, if you take a simple cubic or body-centered cubic or any other diamond type structure, for any other structure, the packing fraction will be always less than 74. Okay, so this is the highest packing fraction, and the highest packing fraction is we get a highest packing fraction for FCC and HCP also. Okay, so this is the atomic packing fraction for a face-centered cubic structure. Now we are going to calculate the atomic packing fraction of body-centered cubic. Okay, body-centered, we call it BCC. Face-centered cubic FCC, body-centered cubic BCC. In the body-centered cubic, we know that the atoms are occupied at the corners, and also we have one atom at the body center. And here, the first let us derive the expression for R and A relation. Okay, first let us do it. Here you can see that the atoms at the corners are not touching each other. Atoms at the corners are not touching. In the last class also I have explained it. Here what happened? The body center atom, this atom and this corner atom and this corner atoms are touching each other. Similarly, if you draw a body diagonal, say, these body diagonal atoms are touching each other. Body diagonal atoms are touching each other. Body diagonal atoms are touching each other. So in this figure, this is the body diagonal, not a face diagonal, not a. Imagine that it is passing through the body diagonal. Here there is no face center atom. It is passing through the body diagonal. So body diagonal length, if you calculate it, we will get it. Look, here I will show you. This is A. You know that this is A because it is a cube. This is A. And this is also A. And the face center. Face center, we have multiple, we can. Face center is rooted to A. Rooted to A. Now, this is also face center, rooted to A. So now, if for a body center, we have actually, look, for a body center, this will be the one side. For a body center, I am drawing here, showing in the 3 dimension is difficult here. So we have an height. This is a face center. Imagine this is a face center, this part, rooted to A. And this becomes the body center. Here, let me use a different color. Green color. This is the face center. This is the height A. And this is the rooted to A. So, face center and height and body center. This become a right angle triangle. So rooted to A. So this become under root of square of this. Square of this become, its square become rooted to square 2. A square, A square. This square become A square. So this become 2A square plus A square. So this become root 3A square. So this is equal to root 3A. So body diagonal length for a cubic, if a cube side is A, then the body diagonal length in terms of the cube length is cube side length is root 3A. So we can write here body diagonal length, body diagonal length is root 3A in terms of A. Now in terms of R, what it will be? In terms of R, this is R, and here is another R, here is another R, and here another R. Because inside a full sphere, so full sphere means the full diameter R plus R, 2R. And at the corners we have an R only, because half part is in the one atom. Because you can see that this length will be R. Here also we have this length is R. So we have R plus 2R plus R. So equal to 4R. Okay, so in terms of r, the body diagonal length is 4r. In terms of a, it is root 3a. Look, in the previous case for face center, face diagonal length in terms of r is equal to 4r. In terms of a, it was root 2a. Face diagonal, body diagonal length is root 3a. So here we can write 4r equal to root 3a. So r equal to root 3a by 4. Okay. Now let us calculate the volume of atoms. So body center, how many atoms we have? From the corners we have one atom, and from the body center, because body center atoms inside the unit cell, it is at the center of the unit cell, that atom is not shared by any other unit cell. So we have one contribution from all 8 corners and one from the body center atom. So total 1 plus 1 is equal to 2 atoms. Total number of atoms per unit cell is equal to 2. So now the volume of atoms is equal to 2 into 4 by 3 pi r cube. Here r value is this. So I am writing it as 2 into 4 by 3 pi into r cube. Look, root 3 into root 3 into root 3. Root 3 cube is equal to root 3 into root 3 into root 3. A cube 4 into 4 into 4. If you write in this way, you can easily cancel it. Okay. Root 3 into root 3, 3. That 3 and this 3 get cancelled. Okay. This 4 and this 4 get cancelled. 2 by 4 equal to 2. 1 by 2. So in the numerator we have pi, root 3 and a cube. So root 3 pi a cube. In the denominator we have 2 into 4 equal to 8. So root 3 pi a cube by 8. Root 3 pi a cube by 8. And volume of unit cell always a cube. Volume of unit cell is always a cube, because it is a cube and the length of the side is a. So volume of unit cell is equal to a cube. So now APF become volume of atoms root 3 pi a cube by 8 into 1 by a cube. Volume of divided by volume of unit cell. So by a cube. So here a cube get cancelled. So this become root 3 pi by 8. So root 3 pi by 8 is the APF of BCC. So APF of BCC equal to root 3 pi by 8. If we substitute the value of this pi, this value become 0.68, and this is equal to 68% in percentage. So for a body-centered cubic structure, 68% of the volume is occupied and 32% is vacant. Okay, not all this point. So okay, so the atomic packing fraction related class is over.